Hello everybody. I welcome you to our speech, which is about finding vulnerabilities in source code and binaries. And this is Halvar, I'm Scott. And we will split the speech in two parts, Halvar doing the binary part and me doing vulnerabilities in source code. So first some organizational things. If you have any questions, just raise your hand and we will answer the question as soon as possible. The speech is about 1 hour. Let's see. And yeah, we will show some bugs and they are either fixed or known or unpopular and not exploitable. So it's nothing really hot vulnerability types. Okay. The first question I would like to start with is why are there source code security bugs at all? First, if you start programming, you usually do not know the entire language and start by trying out trial and error. You fix the compiling errors and so on. And this lack of understanding results in bugs which work on your place. On your place, the code works, seems to work fine, but an attacker might modify the data so that can attack it. Then another big part is that security is usually not a focal design point. It's often added later or not at all. And therefore, because security is so important, it can work out bad if it's not designed in from the beginning. Then another topic is code evolution. Code is not written once and then just used, but code is well, evolved like over years, and code is added, removed, commented, changed, and so on. And this might create a situation where one programmer assumes a certain thing, and the source code later changed, and therefore the thing is broken, and this results in security bugs. Especially in open source software, it is that there are lots of authors sometimes. There are diverse authors from over the whole world with different experiences, and they may create security bugs by working against, like one changes there in the source code, one changes there, and this creates one security bug. Then another thing I will show you today is overcautiousness, like people who fear security bugs and are not really knowledgeable, add margins, safety buffers, and so on, just minor sub there or something, and this can create security bugs too. But the last and I think most important thing is that the mentality, like if it works, I don't look at it again. And this creates a lot of security bugs too. Okay, in source code, how does the language play a role in security bugs? The fact is most used programming language were not built to program securely. They were built with other design goals, and therefore security is only added later, or not at all. And most common languages are also old languages, like old languages not designed for security. They are still used, and old languages are very type intense. You have to type a lot of code, not like in Perl or Python, but you have to type a lot of code, and the more code there is, the more bugs can there be. Okay. We will focus on languages here only on the NCC language, and on architectures we will focus on the x87,
x86, and sorry, I will go into some C++ stuff as well, so it's not strictly NCC, but like 19% is NCC.
Okay.
Sorry.
Well, the fact is, another fact is about NCC, that its basic C library is very diverse. Like it has evolved, standardized, later changed, add-ons were created, and so on. It's different to use. There are like many types where the logically the same thing has been used in 3 different ways. I will show you later. And another thing is that C does not enforce a good style like Python does. Like if Guido wants to indent it the certain way, everyone has to do it, and C is not the case. It's a syntax language, and you have to, you're free to indent it. Okay. We will discuss 4 security bugs, or types of security bugs. First, a rather unrecognized type, the signedness and witness vulnerabilities, which happen if certain types are changed to other types. In this conversion process, there can be bugs. Then, known vulnerabilities as off-by-one, adjacent string vulnerabilities, and last but not least, format string vulnerabilities. Okay, I will start with the first one. It's a signedness vulnerability. And to do that, I will introduce you to the basics of C types. There's an integer type, and it's for anything in C you can count or subtract, add, so on. There are two types of integers, the signed, which covers positive and negative numbers, and the unsigned, which covers positive only. So the thing is to realize how these numbers are represented, actually in the memory, because the security bugs, the signedness and witness extension happens at the very low level, at bit extension. There's a 32-bit integer, like any ILP32 system, any modern computer system uses. And this is an unsigned integer. It looks exactly the same. All bits have equal meaning, and it's used to count things. It has just a positive range. But on the other hand, there's a 32-bit signed integer. And at this integer type, the highest bit, red marked in this case, is used to denote signed values. This will be important later. So 1 bit of the whole number represents the signedness of the number. The security vulnerability at witness and signedness extension happens because lengths can only be positive, like there could be no negative lengths. And if you count, there can only be positive values too. But still, people use size and length checks, which are based on signed numbers, on negative numbers. And how can a string have a negative length? So if people actually write code where they use signed string lengths, they may create security vulnerabilities. So to summarize it, size and length checks should always be unsigned. The definition of a signedness bug, as we will present it, is if an attacker influenced value, a value an attacker can set or modify, has a highest bit set, the signed bit, and is treated as signed value in a length check or in a boundary check, then a signedness vulnerability is present, because a length is taken from a signed value. Examples we will show, too new, too old. The signedness vulnerability, there was a famous loft anti-sniff vulnerability. They messed up 2 fixes for it, and only the 3rd fix finally fixed the real vulnerability. So this demonstrates maybe a bit that even loft can make errors 2 or 3 times. And the other thing is a new bug in Solaris 2.8 in tnamed. I'll explain that later. And witness vulnerability, which is a sort of related to a signedness vulnerability. I have 2 examples too, one new, one old. The old SSH CRC 32D attack vulnerability, which was discovered and disclosed in January, I think, or February. And a new vulnerability in the Linux 11 loader. So, now to the real code in our talk. This is part of the source code of Solaris 2.8 in tnamed. It's an obsolete name service daemon. It's even commanded in the initdconf file as obsolete, but still it's enabled by default on Solaris 2.8. I think no one here has ever used it for anything meaningful. And the interesting thing is that this daemon has, in fact, a vulnerability in the source code shown below. So first, this is real source code. So I will show what's happening. In this line, there's a packet read from the wire, a user-supplied packet. Just read. And look where it's read to. It's read into a signed char buffer. Into a buffer, which is a pointer which points to a signed char buffer. And from this buffer, from the second char in this buffer, a value is taken into a variable called length. And if you notice the type of the length variable and the type of the buffer, then you will notice that both of them are signed. So what happens here if a signed char is extended to a signed integer? What happens is a sign extension, like a negative value is converted to a negative integer value. And for example, the binary here in hex 19 becomes minus 112 in the length, in an integer variable. And as we noted before, lengths and sizes should only be positive. In this case, it's negative already. Oops. Yeah, and you see the converted value, which is negative now, is then compared against the buffer size, which will be later used to copy something. And normally, if the length value would be unsigned and would contain a proper positive value, then this check would be perfectly valid. It would stop all overflow attempts. But in this case, length is negative, the comparison is negative, and we pass the check, although we supplied a negative value. And as you can see later, there's a string copy call, which uses our negative lengths as length delimiter. Negative lengths are converted by string copy to very large positive values, so it's a plain buffer overflow then later, with the cause of the sign extension. Another short vulnerability I will go only briefly into is a Linux 2.4 ELF loader, which loads your local ELF binaries into memory and sets some stuff up in there. And it contains a witness vulnerability. Witness means that through a multiplication, shifting, or whatever, a signed value is overwritten. As you can see here, the ELF-X structure is user supplied. So both elements of it are user supplied, and they are multiplicated. Those are 16-bit values, and they are multiplicated into size. Size is again a signed value, and a comparison is made, which fails again. If we supply the right values, make size negative. This value is then allocated, and later is being read into. Like we can read into kernel space as much as we want. Okay, to summarize it all, like how to find this in your source code, how to spot it in other source code. The first thing you have to do is to check comparisons. Comparisons of lengths should always be unsigned, no exception. Then trace user-supplied length values, like on packet procession route functions, on DNS decoding stuff, where the user can supply a length, where you have to trace how the length is taken and processed. Where does it show up again? And another thing is you have to keep the signedness of the default char type in mind. Like every char is signed, but if you read data from users, you don't want to give the characters a signed meaning. You read usually bytes, and bytes are unsigned. So define them as unsigned.
Whether char is signed or not depends on the architecture.
Yes, that's right, but on most architectures it's signed. And some architectures have, or some compilers have changed their behavior to default the normal char type to be an unsigned type. But most common architectures have signed chars. Okay.
Does this work? All right. Do some switching here. Ja, klar. 1 und 2. Na? Okay. Yeah? Hey, I know what quality is. Anyways, we were just talking about where am I getting the feedback from? Well, anyways, do you hear any strange noises, or is it just my ear? All right. Okay, so we were just speaking about sign bit or expansion vulnerabilities, and we're speaking about the standard C types like int and char, in most cases being signed, and the complications which can arise from that. And as most old school assembly programmers know, you can spot these things not only in the source but in the binary as well, or in the disassembly at least. And generally a good advice to programmers in general is to always use unsigned values unless you specifically want a signed value, because there's just too many screw-ups if you try to only identify those cases where the signed value could be dangerous. So better safe than sorry. Anyways, Scott was speaking about well, the expansion of like signed chars into larger variables and so on. And the disassembly, it's actually quite easy to spot, as there are basically only two instructions in the x86 architecture which expand a smaller value like an 8-bit or a 60-bit value to 32 bits, which are the move SX and the move ZX instructions. A few other instructions exist, but they are not used by compilers usually, so like in standard compiled code you'll not find them. So move ZX means move with 0 expansion. This would be an unsigned value. If you have like an 8-bit value, say 80 hex, and it's being expanded to 32 bits with a move ZX, it will be expanded to 32 bits and it will still be 80 hex. So it will take, well, it will just expand the value to 32 bits, and all the new bits which have not been there before will be padded with zeros. Sorry if my speech is a bit slurred. I've just finished my military service last week and I've been partying a bit too much. So on the other hand, we have the move SX, which means move with sign expansion. And in this case, or I don't know whether it means move with sign expansion, but it sounds plausible. So this will take the uppermost bit in a byte or the uppermost bit in a word and expand it all the way through the rest of the value until it reaches 32 bits. So basically an 80 hex value will be expanded to FF80, which is quite a long string to append. So basically if you watch out for the move SX instead of the move ZX, you have a good chance of finding problems. Let's see whether Internet Explorer actually works. Hey. Scott mentioned the signedness of comparisons as well when it comes to length checks and the like. Well, unfortunately, most programmers these days don't really know anymore that there is something like an unsigned variable and a signed variable and so on. Basically, the two families of branches which exist on the x86 architecture to branch after comparison are the above, below, or the greater, lower ones. And if you see, wait a second. If you see a jump above and jump below, you're dealing with unsigned values. If you see a jump greater, jump lower, you're dealing with signed values. So if you see some kind of length comparison and then a check for a jump greater, jump lower, you know that the programmer fucked up. Oh, further? Well, this is too far. Gotta switch back, I think.
Okay. Well, the next thing is, okay. Okay. Next thing is how C and other languages treat buffers. And as you all know, there are char buffers. And here's an example char buffer of 8 characters in size, and looks quite simple. Next step is how these elements are referred to, and what's quite unnatural to non-computer people is that the buffers start counting at 0. And although the buffer has 8 elements, in this case it only has elements 0 to 7. And this is why a lot of programmers even, or beginners, tend to confuse buffer lengths, string lengths, and so on at the end of the buffer. We'll see later. So the element behind the buffer is a off by 1 element, and is the nth element of the buffer. So if the buffer is defined as char buff 8, then the 8th element isn't actually in the buffer anymore. It's one outside of the buffer. So there are multiple behaviors how a program can treat the buffer. This is the proper behavior. The string should always be terminated, and the string may not contain more than n-1 elements. So there's one element left for the terminator. The termination character is the null character, and this is the proper behavior. The element behind the buffer, the nth element, is not touched anymore. The adjacent strings behavior is a bug, but often goes unnoticed because there isn't anything overwritten behind the buffer. The buffer remains just not terminated. And if you're lucky, there is a null character just behind the buffer, and you won't notice. So it's a bug that often goes unnoticed. You see, there are 8 elements in the buffer, and the termination character is missing. Kommt nachher. Okay. Well, the most dangerous behavior is the next, the off-by-one behavior, where programmers confuse up lengths and sizes, and somehow the code happens to store a terminator element right behind the buffer, outside of the buffer, in the nth element, in the red marked element. And why are these off-by-one vulnerabilities so interesting? The C index counting starts at 0, while natural counting starts at 1. So there's a natural confusion behind this. Although you may, a logical person may say, counting starts at 0, that's natural. It is not natural to our common day thinking. Then another thing is that C string and memory functions are diverse. If they have length values passed to it, the length value may be treated differently depending on the function. And, yeah, well, I will show the 3 meanings of length in C, in the C RP, in the libraries. There are 3 different interpretations of length. For example, strncut is the worst of all. You pass a length to it, and it will store length elements plus a null byte. So if you just store size of buffer as length, you already have made an off-by-one vulnerability. But the natural solution is not to subtract 1 from the length. I will explain that later too. The proper behavior, like you would expect as programmer, is the behavior of the snprintf function. It stores n-1 bytes and always terminates with null. And the last behavior may generate adjacent strings. It zeroes all bytes with null, like if you pass length equal to 8, it zeroes all 8 bytes out, but then adds up to n bytes. So the buffer may remain unterminated. And that is bad too. So there is a confusion about off-by-one vulnerabilities. The unnatural counting and the different meaning of the length element, length parameter passed to string and memory functions results in a bug which may store a null, a termination character, to that element outside of the buffer, to the, in this case, the 8th element, which is not part of the buffer anymore.
No, this is not the blue screen of death. Okay, well, we've spoken about off-by-ones for a bit. And basically, almost all of the traditional off-by-ones, the strn copy, which does not null terminate, the strn, which writes a null byte behind the buffer, the scanf, which writes a null byte behind the buffer, and so on. All of these can pretty much be, well, determined more or less, depending on the answer to the question if size of target buffer equals length. If you can answer that question, you can usually answer whether this is a suspicious construct or dangerous or not. So if you're dealing with a binary, we have the small problem that you don't have a size of buffer anymore. all buffer sizes are pretty much lost. You don't know what's going on anymore. Everything is memory, and well, you have to kind of guess or figure out how large those buffers originally were. And this is where something comes into play which is called buffer size estimation, where you basically analyze the assembly for accesses to a certain pointer, or like references from a certain location, and an offset from that, like you take a location 20, assuming there's a buffer at location 20, and then you add 5 to it, and that's accessed again, so you can guess like the next buffer after the first one starts 5 bytes later. And actually, when you're dealing with stack buffers, the disassembler IDA Pro will handle pretty much all the buffer size estimation on the stack. You'll not have to worry about that. And it will handle a certain degree of buffer size estimations in the static heap as well. What it will not do is any kind of buffer size estimations in the dynamic heap. So any kind of structures or objects which are allocated runtime and which are used, well, are pretty much unknown territory for you. So you really can't audit off by ones without being able to reconstruct structures. And this is an incredibly annoying and time-consuming process. And in order to give all of you an idea how extremely annoying and time-consuming it is, I'll demonstrate it for about 5 minutes. So, okay, so this is some kind of NT SMTP daemon in the disassembly. This is IDA Pro, by the way, a tremendously good product. Built by some Russian dude who's now living in Belgium. And just go out and buy it. All right, so we see the main command handler here, up here, where you, wait, I think you even have a laser pointer somewhere. Aha. All right, so this is the main handler here, on the beginning of the main handler function. And here we see pretty much the stack layout IDA has reconstructed. It hasn't assigned useful names because they've all been lost in the compilation process, but it has pretty much reconstructed the buffers on the stack. So let's have a quick look at that. Hello, where's my mouse cursor? Ah, here it is. So on the stack, you have a pretty good idea of how large buffers are. For example, file name seems to be 180 bytes large. Now, what we do have in this case at arg4, the second argument to this function, it seems to be a pointer to a structure, as down here we can see a lot of moving this pointer into a register and then adding an offset to it. So this is most likely a dynamically allocated structure. And what we can see here is that there is probably a structure member at offset BO8. And well, I was about to show you something boring and annoying. So we'll start. We pop up the structures window. We create a new structure. Let's call it unknown structure. Then, whoops, we add the first byte, and then we add an array of BO8 hex bytes. Does this work? Remove the H. Let's try it like this. There we go. So you can see I didn't rehearse this too well. Actually, I screwed up one second more. 1 second, please. Okay, there we go. So now we have a new structure member at offset BO8. And we can go down here and define this as a structure member of our unknown structure. And now we have one structure member. We don't know how large it is yet because we have to reconstruct the entire structure to figure that out. So we go down. Hey, we have another one down here at 1308 hex. So we go into the structures window again. And this is going to take forever and forever and forever, because now we have to calculate BO8, well, 1308 hex minus BO8 hex, and add another structure member there. So I pretty much decided at some point that my time is too valuable for that, because I prefer doing other stuff than sitting in front of the computer. So I wrote a small program to basically parse all access to a pointer and reconstruct the structure from there. So we'll just quickly run it through this. we feed it the pointer. Whose cell phone is that? Okay, so we feed it the pointer. We feed the name of the structure we want. And then we pretty much hit enter. The recursion mode is not implemented yet. Okay, so now we hit Shift F9. And here we have the structure, which is quite nicely reconstructed so far. Actually, okay, wait. While I'm at it, I might as well demonstrate how we can find an off by one, or at least a coding mistake easily, now that we have a reconstructed structure. We go to the location of the lstrcpyna, which is Microsoft's perverse name or perverted name for strn copy. And we have a look at those calls there. There are 22 calls to this function in the binary in total. We go through this. Here we have a static value for the length. So, oh wait, no, this is not the right, well, bullshit. Forget it, I was talking crap. Anyways, we have a stack buffer here, and we pretty much know that IDA can reconstruct stack buffers, so we're not going to get into this. We move down 5 rows, and here it is. We have an strn copy inside a structure, and we see all those offsets here. So we just run my little program again. There we go. Now we have all the structure members defined. And what we can do now is we can go into the structures window and collapse all the, wait, I'll scroll up a bit, and collapse all the members so we get actual buffer sizes. Now this looks a bit more usable and actually good for estimating stuff. We got quite a few double words in the structure and 2040, well, probably like 48 buffer, a byte buffer and another one, and 255 byte buffer. Actually, my computer is responding quite slowly today. Oh well.
Because it's Windows.
Fuck you. All right. Sorry? Oh, well, yeah. I didn't take it with me to parties, so it has no reason to be slow. Okay, so what we see here is that the strn copy is targeting this buffer here, up there, unknown 1C18. So we can see here that this unknown 1C18 is 64 bytes large. And then we can see as well that the max length parameter passed to the string copy up here is 64 as well. And what do we know about strn copy with the target buffer size equals to the length parameter? No, it is not no terminated at all. This is strn copy, not cat. Pisa now owes me a beer. All right. Any questions concerning this so far? No. Actually, there is a public script which I've published a while ago, and there is an old version of the plugin as well, which is not quite as powerful. It tends to hang from time to time, but you can get, well, at least the source of the script and the source of the old plugin. Just ask me, send me an email. Sorry? No, that's strn cat. This is strn copy. No, strn copy zeros. Oh. Oh yeah, yeah. Actually, we do have that. Probably, I'll have a look at that. Yeah, they do that. Yeah, but the thing is that they might be actually copying stuff into this buffer later on. But it's true that I have never claimed this is exploitable. So, well, we can't disclose all that much ODay here. Seriously not. All right. Where was I? I was ask a question, whether there are any questions, and I'm done with that now. Okay. All right. Now, we'll move on to some more interesting stuff. If any one of you has ever looked at the disassembly of IIS, it's a complete freaking mess. 30% of the code in IIS is dead. It never gets executed and it can't be reached at all. It's quite annoying when you audit stuff the way I do, because I identify the suspicious functions first and then I trace upwards. And then I'm like, hey, I got like 10 format string bugs, and none of them can be reached at all. And can be quite frustrating. Furthermore, Microsoft has developed some insane kind of optimization where they move less well-trodden code paths to different pages than well-trodden code paths. And therefore, you have not one function on one memory page, but you have parts of one function on a different memory page, somewhere completely else in memory. So it gets an insane mess. That's what I was thinking when I looked at that as well. So, well, furthermore, it's object-oriented, and with object orientation, you're pretty much screwed because you don't know the layout of the class data structure, so you don't know any buffer sizes. But basically, what exactly is a class? A class is pretty much a structure with a bunch of methods, functions associated with it, and they all operate on the same structure. And with the structure reconstruction, we have seen that the more functions we get which operate on the same kind of structure, the more accurate our rebuild gets. So in case of object-oriented code, we frequently have something called vtables, where all the virtual functions are stored, which is basically good for us because it's a list of functions which all operate on the same structure. So I'll quickly load up the core web server of IIS into my disassembler. Probably not so quickly, but I'll load it anyways. Whoop-de-doo. Okay, we got the vtable for the WAM request class here. And it's just a collection of functions. And this one is rather unusual because it actually is not some kind of insane C++ optimized Visual C crap, but is actually readable. So we got the this pointer as the first argument to all these functions here. And we will just run my plugin, like the old version of the plugin, which I'll give out, does not do object reconstruction at all. The new one does vtable parsing, so this is the stuff that I don't want to give out. You can have the old one. So we run this over the vtable. And arg0 is this pointer to the object. And we call it WAM rec. And we don't want recursion, mainly because it doesn't work. So this will take a while. Well, it'll take a while, not forever. I think we're pretty much done. The third person is going to eat it.
Yeah, that was good military training.
Makes you a very tolerant person. All right. So here we got the reconstructed class, and we can see that my code is not good because I don't think this is a reasonable size for a structure. So it probably fucked up at the end, screwed up. Actually, we're not in the States. I can say fuck here, can I? All right. Anyways, we'll just collapse all these things and then fix the end, so we get a nice idea of what the WAM rec looks like. So you can see it's mainly a collection of pointers with a few smaller buffers. Hello? Okay. Okay, what we can see here is that we probably have an array of other structures inside of our original structure because, like having a combination of 44 bytes and 4 bytes after each other several times is not something that normally would happen. So probably they have some structure which contains 44-byte buffer and a pointer, and they have an array of this kind of structure inside their class. So as you can see, we get quite a nice representation when we ignore the end, and we will quickly fix that as well. Okay, so we can see that this has saved us quite some work, and we can now have a reasonable estimate of how large buffers are and what we're dealing with. I'm not saying that it now doesn't make me vomit anymore to read that code, but it's at least a lot more doable than before. Okay, so I think that was pretty much it when it came to object and class reconstruction, wasn't it? Yeah. All right, so I'll hand the microphone back to Scott. Any questions so far? None? All right.
Den links zu euch. Ja. Thank you, Oliver. Okay. So next topic is being too cautious. Well, sometimes it happens that programmers fear security vulnerabilities in their code, like BSD people or something, and they happen to add a safety margin to buffers, to lengths. They subtract constant values from lengths, like to be sure I have 4 bytes left or something. So you have to have remaining space to store terminators and so on, not to have to worry anymore about wrong length parameters. And sometimes they do it wrong. This is an constructed example of how being too cautious can be wrong in code. As you can see, there's a buffer, 256 bytes long, and there's a string copy, which does not terminate in the beginning with a user-supplied argument. But that's not the real bug. The real bug is below. The bug below would behave properly, except if you see the sourceandbinarysecurity is used to append stuff to the buffer, the second parameter to the main function. Oh yeah. Oh. Well, you see here first a buffer is copied into the temp buffer, and it's not terminated. And later in the sourceandbinarysecurity function call, yeah, there's data appended to it with a length that's constructed here, and the length is constructed by subtracting the size of the buffer minus the string length and -1. So actually the -1 is a fault. The length may get negative here, and negative lengths past the string functions usually result in the length check being disabled. So this stuff is appended to it, and the buffer overflow may happen. But this is a constructed example. I will be more happy to show a real. Yeah. If it. Oh. Oh. Okay. Well, I see. Okay, I'll see. We'll discuss it later. I have a better example, a real example of real code, which is. That's a stupid constructed code. Yeah. This is a real example, like latest pro FTPD code. Not exploitable too, but interesting. And there's an assumption that this condition is true. And you see, here's a buffer, name line, which has a certain length. And into this name line buffer, there's user-supplied input printed into it. File names. It's a ls module. And later, a pointer is used to append data to the buffer. And here you can see a nice length construction. The size of the buffer is subtracted with a string length, which would usually be correct behavior. And then -4 is subtracted, because later they append extensions somewhere here in the code. And if you see that if string lengths get long enough, then the whole length will get negative through it. So a negative length is passed to sourceandbinarysecurity as length parameter. And this is then usually sourceandbinarysecurity buffer overflow, because the length check has been disabled. Yeah. Yeah, that's right. But sourceandbinarysecurity Well, SNPRINTF gets passed a negative length parameter here. So SNPRINTF appends and thinks the buffer is gigantic large, like -2 billion characters long, because the negative here is the value passed to it is negative. So
Name line has a size of has a certain size.
yeah.
Remember the name line is being written by the SNPRINTF, and you said
The first one.
Yeah, the first one. So you said that SNPRINTF obeys the size restrictions. Of
Yeah, it's the first SNPRINTF is perfectly same.
It puts the buffer almost to the brim, like almost to the end, and then the string length of a name line is like, let's say, 2 bytes less than the size of the name line. If you have like this evaluate to 2 and then you subtract 4 and then round it to the negative. So that does have nothing to do with improper.
So this subtraction may get 2 as result, and then 4 is subtracted from 2, so it wraps around negatively. So a negative length is passed to it. Okay, we will get to the next topic, which is you.
Actually, I Is it?
But the problem is that
the problem is
expect an unsigned length value.
no. The problem is that somebody is subtracting too much from a place where there isn't enough. The problem is that he's subtracting 4, like string length of something, if it's properly terminated minus size of, can only evaluate, like can at maximum evaluate to 0, and there's no need to subtract anything from it.
Yeah, that's true.
So basically the subtraction is the fact that it wraps around. And it is true that in general it's a problem that many of the functions use a size t value, which is unsigned. But it wouldn't fix anything to make it signed either. You could check whether it's negative. Yes, of course, you can add those checks in the library, but we all know that there are buggy compilers and about 20 different specifications of, well, there's one specifications, but very many different dialects of C. So we have to hurry a bit because we're running out of time.
Yep.
All right, subtraction problems. Scott mentioned before that subtractions can be potentially dangerous, and we've just seen that. So basically, any memory copying function in the C library which uses a size t as length parameter, and which subtracts something from this length parameter prior to passing it to the call, has to be considered suspicious and should be investigated. So something like this here, where you load a variable into a register and then you subtract something from it, and then you pass it as length parameter into a memory copying function which uses size t, has to be considered suspicious. And to sum things up concerning cast screw-ups and signness misconceptions and subtractions and so on, if you follow these guidelines in auditing binaries, you will find lots of stuff. Basically, first you check whether the size t of a specific memory copying function is dynamic and not static. If it's 200, you're not really interested. Furthermore, well, if it is dynamic, you check if it's loaded with a movesx instruction, or if it is accessed with sub or dec instructions before it is being passed. And those are basically the criteria you should look for when you look for cast screw-ups in the binary. And when it comes to faulty comparisons, well, just stick to the slide number 2.
Thank you again. Let's see. The final topic we have, and we have 10 minutes left for it, is format string vulnerabilities. Yep. It was disclosed like mid of year 2000 as a new type of security vulnerability. Has been a shockwave. Has released a shockwave of new exploits and new vulnerabilities being discovered. It's popular in all kinds of Unix applications, and it's particularly interesting to exploit. And more interesting, it's really able to find and identify them automatically. So not like buffer overflows, which usually require like auditing the code line by line. This type of security vulnerability can be found automatically. Quick introduction. Here is a correct behavior of a format function and an incorrect behavior. You see, user supplied input, denoted as user in a variable, is passed to the printf function. One time as second parameter, the other time as first parameter. And in this later case, it's done wrong, because the user supplied string shouldn't be the format string to the format function. There are two main reasons why this would occur in real software. First, there was this news that some syslog functions could not handle more than 6 parameters, or could not handle some certain format parameters. And so people tend to use a printf into the buffer, and then pass the buffer directly to syslog. This is one major cause for format string vulnerabilities. You see, the string temp is passed as format string to syslog function. The second, also common reason why there are format string vulnerabilities is that people tend to think, this is my output function or my log function or whatever, and I just want to output that. They don't think about how the output is processed by the function, they just want to output that. And in the majority of the cases, it just works fine. But if an attacker can modify the string, he can use it to compromise the process. One example why this is not so easy to spot manually is the WU FTPD site ESEC bug. You can see there's a parameter, the parameter CMD, which is user supplied completely, passed to the areply function. The areply function is a format function on itself, like here, and it passes the format string again to the vreply function, and the vreply function finally uses vsn printf to output it, use it perfectly. Uses passes the format parameter which was originally supplied by the user. This is exactly the same string, the CMD and the FMT string, to the vsn printf function. It's a format string vulnerability. So to quickly summarize it, how to spot format string vulnerabilities in source code is to trace every user input through the entire program, like from the input function, how it's processed, to the output function. Then pay attention especially to the log and output functions. This is where format string vulnerabilities usually happens. Syslog is used to log it, or output is constructed and then sent back to the user. Check every use of the common format functions, like printf, sprintf, and so on. And finally, I said it could be identified automatically reliable. That's true, you can use tools such as pscan or custom tools, which are more effective, but it's proof that you can find format string vulnerabilities completely automatically if just one would write such a tool. Okay.
So I'll try to kind of rush through the end of this. We only have 5 minutes left. Who's speaking after us? Will he be mad if we do overtime? That format string bugs are an argument deficiency with a dynamic format string. That's the basic definition after which I use to automate the finding of format string bugs in binaries. And well, after this definition, I'll just move on a bit. Okay. First off, the question is, how do I determine whether I have an argument deficiency in a certain call? On the x86 architecture, we have something very useful, if the compiler hasn't optimized it away, which is called the stack correction. After every call, the ESP register has to be adjusted. The stuff which has been pushed before the call here has to be cleaned off again. So they add a number of bytes to ESP. So basically from this, you can learn how many arguments a certain call had. In this case, you can see the STR copy had 2. And, well, yeah. And you can calculate the stack correction like this. 2 arguments of double word size 4 is 8. Security really isn't that hard. So just an example of the stack correction arithmetics with printf, the argument deficiency would mean 4 bytes, sprintf would mean 8 bytes, smprintf would mean 12 bytes. Is that clear to at least 40% or all of you? Okay, it's not that, like, it's pretty basic. So basically you can completely automatically scan for format string vulnerabilities if you use these criteria. You basically identify all the functions which belong to the printf family, also those wrappers which use vsprintf, vsmprintf, and so on. And then you check every single call to them whether the format string is dynamic and whether they have an argument deficiency. And I've written an IDA script for that, which you can have as well if you send me a nice email. And that scans for format string bugs, and I'll quickly go over something because I got a nice disassembly of checkpoint firewall here. And we got a vsmprintf call here, and there's 32 vsmprintf calls in total, and I'll just rush a bit because at this fifth call, we have a function which is called quite a few times, like a few hundred times throughout the entire binary of firewall 1. So I'll run a quick IDC script. Eine Minute? All right. I got 1 minute left. So we'll not go into the exploitation. I'll just show the bug. Okay. We scan at this address where the function is at, A5B0. We got 3 arguments, so the stack correction should be 12 at least. If it's lower than 12, we have an argument deficiency. And usually the second last argument is the format string, so in this case it's 2. We let the script run. It'll take a while. Okay, it's done. And now it has highlighted all the format string problems in firewall 1 in this particular function. And at the very bottom we got this one, which is, actually it is exploitable, and Checkpoint has fixed it recently after we had a nice conversation with them. And basically when you have the management client, like the log viewer or the policy editor or whatever, connect to the server, you pretty much, well, they send commands, and they are filed in a big hash table under the name subject here. So what's happening here is that if you send an unknown command, it first outputs this error message. Basically, it syslogs this with the %s here, which is perfectly valid, takes the value from the hash table lookup, and then it just passes what we got here down here into our function. And basically, if you send, instead of like the first command the client sends is called log database, and if you send a format string instead of that, then, well, you can execute arbitrary code. You have to be authenticated as at least somebody who has the permission to view logs, so it's not like you can go out and own your bank now. But you've seen the number of format strings which are still there. Anyways, normally I would demonstrate it, but time's over. So any questions concerning this? If not, then thanks for your patience, your time, and it was a pleasure meeting you.